And today I'd like to use more than an hour to talk to you about what we have done related to energy and the sensor system, what our discovery is. And I also like to tell you what are this discovery going to impact fundamental chemistry, physics, engineering, even commercial product. So give me some time to do that. Right? Let me see if this works or not. Okay, not just that. Okay. So when you talk about triboelectricity, it has been known for 2,600 years. Everybody knows. Triboelectricity and tribology has made three major impacts to human history, civilization. Number one, we make how to make a fire, how to make a cook, right? Cook meat tastes better than raw meat. Number two, transportation. This rolling transportation was discovered. They found have less friction compared to sliding friction. Number three, more importantly, through study of electricity, people find electrons, charges. So this is the beginning of the power we are benefited from today. So you can see a phenomenon we know for a long time. We have been utilized. Then you probably say, what's new here? I can tell lots of new we do not understand. Even to chemistry, I'll tell you because this is a department of chemistry or biochemistry. All right, so give me a little time. Now, if you talk about electricity, so many outstanding scientists, Danish scientist Ørsted, and he, 1820, he was studying the relationship between current and the magnetic field, and he found this Ørsted's law. Later on, MP make it mathematical expression. So this is set the fourth equation for the Maxwell equation as the beginning. A few years later, Faraday defined electromagnetic induction. 3 years later, Lenz make it a mathematical expression for the Maxwell's electromagnetic induction. So those two form the third and the fourth equation for the Maxwell equations. Okay, we know Maxwell equations, but it's not only one person made contribution to this. There's a few key faculty in over 100 years ago that made an outstanding contribution. Two of them I would like to mention. This nice form was not the form Maxwell put in the first place. It was made possible by Heaviside, this scientist, in 1885. By that time, Maxwell already died for 6 years. Okay, and later on introduced discipline vector by Larmor, such and many other scientists too. Experimentally, it was first proved this was correct by Hertz. Okay, so this is a brief history show the important milestones made in people realize the relationship between electricity and magnetism. We are beneficial from them now. Okay, so then I talk about this one. You say triboelectric has been around so long time. What's the update started? Even 300, 600 BC, people realized triboelectricity, ancient Greek time. Later on, they ranking the materials which have more positive charge or less charge 2 centuries, 3 centuries ago. Until recent centuries, they start electrostatic charges, build a machine for that. The mechanisms related to the triboelectricity only been reviewed in the last 20, 30 years, not very long ago. So we knew the phenomena, but the understanding is still under study. Okay, so without go to the detail of this one, the reason I introduced one is our discovery is indispensable from triboelectricity. So let's say what you do. If you look at the challenge we face now, the whole thing faced humankind in the future is energy. Okay, we rely on coals and oil-based, gas-based, etc. All this is called fossil energy. Then you can see how much fossil energy do we use per year. Let me tell you. If you can see in the last 20 years, the amount of fossil energy utilized increases exponentially. So he said, if this continue like that, how long we can sustain? According to this survey, they find coal for the world is enough for 130 years, oil is 54 years, gas is 49. Not very long. So pretty much say by end of this century, fossil energy will pretty much run out. So not very long, not much time we left. So energy will be a constant challenge, a forever challenge to the sustainability humankind. So from my research last 30 years, what we can do to be able to help the people to use some of the energy in our environment. So that's our research. So today's talk mainly in 6 parts. First one, high entropy energy. You probably never heard what is called high entropy energy. Let's look at today's energy system. We burn coal and oil, we generate electricity, power grid send this to 1,000 homes, so we utilize that. So this is today's power technology we use. Then, according to the first law of thermodynamics, conservation of energy, where the energy go can be dissipated in the environment in the form of heat or mechanical. There's no wonder you feel weather is warmer every year. Of course, globally, how much fossil energy we have burned. Okay, so but today's society is not only for house use, it's called distributed electronics, sensor network, artificial intelligence. So this is from fossil energy concentrated, goes this distributed energy, some kind of disordered, even wireless. So we call this the energy for to meet this by the distributed energy we have around us is called high entropy energy. So this was the concept. 20 years ago, we started on small energy harvesting. So my goal has been how do we meet the need of micro devices? So that was started 20 years ago. Today, you have solar energy, wind energy. Put all this together can be called high entropy energy. So high entropy energy is what? It's about the harvesting of widely distributed, low density, low quality energy in nature that is available at any time in anywhere. Can you use this such energy? So we have lots of energy, but it's not in a form we like to have. So how do we convert that into electric power? That's what our dream. So we call this high entropy energy. Okay. They say what you have done to assist us to do this one. Let me show you. This is almost 20 years ago. That time we was grow zinc nanowires. As the chairman mentioned, I was working nanostructures. So that time we grow nanostructures. I use an EFM tip to trick nanostructures because the piezoelectric effect will receive about 5 millivolts output. Because it's so small, 5 millivolts, the current was very small. So output power is picowatt, nanowatt range. So we call nanogenerator. So the name was because it was piezoelectric nanogenerator. There was a reason for it. And this name still today we utilize, but the meaning, the performance is way surpassed what we have 20 years ago. So we call the name is a historical reason. All right. So this was the beginning. We face the continues to increase the output, so we'll be able to utilize for some purposes. By year 2012, we made a major discovery. The major discovery was use triboelectric effect and electrostatic induction effect to couple together two pieces of polymer with metal foil on top and bottom. We can convert mechanical energy to electric power. And later on, the output is dramatically increased as time goes. So I will show you our work done based on this. You can see this paper was not published in a Nature or Science somewhere. I had a difficulty to publish that first place. And rejected, multiple rejection. Finally was published in Nanoenergy, the journal I founded, the first issue. By today, this paper has been cited more than 5,000 times. It was the first paper in this field. Okay, right? So, or even have 5 modes cover all what we can meet in our daily life. So this is the beginning. Now, then you say this discovery Why is a revolution technology? What you have revolutionized, what you have done. Let me compare. Faraday's electromagnetic inductions, 1831, utilized a metal coil to cut through magnetic flux. You can generate conduction current. This is what we do today. But its output voltage is proportional frequency, output current is proportional frequency, so the output is a square of the frequency. So when the square, the frequency is low, the efficiency is very low. That's why you cannot work at a low frequency. Okay, you have to amplify. In contrast, always triboelectric effect and electrostatic induction effect. And this run at low pace is a high output voltage. You can even you have a low pace, you be produce a high voltage. The current is proportional to frequency, so our power is linear to frequency. Both are different scientific mechanism, different materials choice. This is metal and coil. This is organic materials, polymer materials, and metal foils here. Different materials, different output characteristics, gonna have very different application. So this is a comparison. You say, what's difference? Is fundamental science different? Okay. Now that this is better than this in some case. In which case, if you look at low frequency, you run a low frequency. All the things in our nature is low frequency, low pace. The output of TNG is 10 times of the EMG. If you look at the low amplitude, that means small motion like that, the output of TNG is 3 to 10 times of the EMG. If you look at the conversion efficiency for high entropy energy, you have low input power density. The energy conversion efficiency, this is 3 times of the EMG. So this is just a newborn baby only around us for 10 years or so. Its output in some cases is way much more superior than a technology that has been around for 180 years. So immediately showed us a tremendous thing to offer to us in the near future. So my talk today is focused on the science, technology, and the commercial application of this one. Okay. Then you say, well, when I use magnetic EMG, I have magnets and coils. I don't have much choice about materials. But when you use TNG, you can choose a lot of different materials. You can use oxide materials. You can use organic polymer materials. Literally, you name it, you'll be able to have a broad range of choice. For example, if you work for biological system, you can use biodegradable, biocompatible materials. All this can be utilized for this. So the choice of materials is broad. Of course, the application will be broad too. Okay, so this is show you the material choice. Mostly, importantly, the output characteristic is not in to compete one with the other. Is that complements for high amplitude, high frequency use EMG. This for low frequency, low amplitude use TNG. Both have its own working zone of figure merits metrics. So this is different. And this brings it to offer you something you are unable to do before. Okay, so this is the material choice. Then you say, what's the application? Application is for micro nano energy system, solar power sensors, even for blue energy, and even study fundamental chemistry. Let me start with science first. Okay, fundamental contribution of TNG to chemistry. You say, what does this has to do with chemistry? Let me show you what it do with chemistry. In chemistry, you have a well-known phenomenon, especially in chemical engineering. You have electric double layers. You have a solid and liquid. You have in the textbook it show you have a so-called electric double layer. You have a layer of iron on the solid surfaces, and as a result, the cations and anions distributed in a liquid form a potential drop, which is called electric double layers, which is widely utilized in our many applications for this. But this model is not a complete model. It's only cover the ion distribution around the surface. It did not include the contribution from electrons. Let me show you a detailed study. Even you read this in the textbook, but it's subject to expansion. Okay, let me show you a little detail. This here, okay? And our study is use a standard sample of silicon oxide. And we first one heat it, so we get rid of the surface charge. So this is a virgin surface, no surface, no charge. Then you put a droplet of water on the surface. Then you wait this to dry. After dry, you have a probe to measure surface charge. Immediately jump from 0 to minus 800 microcoulomb per meter square. Jump from here to here. That's the charge. If you this remain in the air for room temperature, it can be the charge can be on surface for a very long time. But now, if you heat the substrate to 393 Kelvin, the build-up charge decay like that. If you heat up 433 Kelvin, it decays like that. 473 Kelvin, it decays like that. It never goes to zero. It's have a residual number, minus 180 microcoulomb per meter square. That means what? These are the residual ion on the surface. These are the electrons you have eliminated. You say, how come? You apply temperature, thermiotic emission, get rid of those electrons. Okay? So at the virgin surface, you put a droplet, the charge density jump over here. After dry, you heat up, you have residual ion. This is this amount. Then the one you got rid of are the electrons. Then in the same area, put a second droplet, the charge jumped over here. Then you wait dry and heat again. This is more residual ions. Third droplet, fourth droplet. After the fifth droplet, you have pretty much of ions. You have very little electrons. That means what? You have to have this cycle, temperature cycle, you be able to reach this. If you don't have this temperature cycle, you have ions and partial electron too. So therefore, the surface dynamics depends ions and electrons. That means in many cases, we see the experimental phenomena we're unable to easily explain because the dynamics of electrons at the surface is different from ions. So this measurement shows that. Okay, is this a universal phenomenon? So we studied it: magnesium oxide, silicon nitride, titanium oxide, and aluminum nitride. Pretty many materials we studied. You find different materials, of course, have different ion and electron. In the first droplet of water with it, different ion and electrons. You can figure out that this chemical absorption or physical absorption depends the material's choice. And this means it's material dependent. Material dependent. Without going to detail, shows that truly you have both ion and electron presence at the surface due to liquid solid contactification. Okay, so this study leads us to have some important understanding about the role of water. Then you say, well, if the water contact the surface, right? You have a water drop on the surface. That's what you do, okay? Nothing special. Then you say the surface have electron. You wonder where the electron come from. Traditionally believe water cannot give electron. That was our understanding at least a few years ago. But now let me show you something different. There was a beautiful study use time-dissolved ultrafast X-ray laser probe. They find water ion. Water can give you one electron become water ion. The only thing, this paper, you do read this paper, the lifetime this water ion is 200 picoseconds, during which the water ion and water molecule combine into hydroxide group and another group. This happened. Okay, this paper shows that our study shows this is true. So therefore, water can become water ion, but it's only a very short time. If your probe cannot catch that, of course, you cannot detect it. So the new technique helps the understanding. So therefore, this does can happen, and this introduces many things in the chemistry. So after we study this for some time, we have proposed a two-step for formation of electric tribology. If you have virgin solid surface, you put a drop of liquid on surface. You have both electron transfer and ion absorption. And for silicon surface, the inter-electron distance is 60 nanometers. Inter-ion distance 30 nanometers. You can measure this quantitatively. This study has several consequences. Number one, both the electron and the ion contribute to the formation of electric double layer. So we have electrons and ions and form a layer. Because these negative layers attract positive ion towards the surface, you form this electric double layer as what we expected. So this is number one consequence. Number two, why do we have to have EDL here? We have electric double layers because contact electrification at the liquid-solid interface. This is the reason you have the EDL. This is an important conclusion, number two. Number three, where the electron come from water molecule. So this study shows these three consequences. I will go slight detail for some of that. Okay, so this is the formation electric double layer. Then, can we study dynamics related to water and the surface charge transfer? So we have an array. This is 433 pixels like this. Each is a TNG. So if you have a drop of water flow down here, the charge is transferred to the surface of PMA, be measured by the TNG at the back. So this 403 is a ray. So you have water flow like that. When you water flow, you have charge exchange between the water and the PMMA. On the back side, this pixel can measure it, and this is the measurement results. You can measure the charge transfer when this water slide down, pixel by pixel. You can quantify it, and this is a probe. TNG is a probe for studying liquid-solid interface. I believe you can study a lot from here because you can have different functions grouped on the surface. This is a technique. It's a technique can allow you to probe that. Okay, so this is just the beginning of use TNG to study liquid-solid interface. This is and most recently, I will remember to this one. They have a not a pixel electrode, but it's a stripe electrode. They put a droplet of liquid on this, and when this slide down here, they measure the charge transfer between the liquid and each pixel here, and then they plot. They got this, and they found this profile is different from different liquid to another one. So they proposed this triboelectric spectroscopy, and this is what we found. We measured about 50 different chemical species. We can do that. And we just published the first paper. Then you say, why is this? What we can utilize for identify chemical species remain to be studied. So this is just as hard as can be. Right? So a lot more work to be done, but I want to point to you. Here's a new area. You should look at that. So we call that triboelectric spectroscopy. Okay, now, why you believe there's electron exchange? Have you measured that? We measured this 10 years ago. By that time, our understanding was not there. If you have a U-tube, when you do experiment, you put an electrode here, an electrode here. If you rotate this U-tube back and forth like that, so liquid level changes back and forth. If you calculate the ratio between the liquid and the electrode surface ratio, because the charge transfer between the liquid and the glass wall, the induction charge on the electrode will change from time to time. So the charge will flow back and forth between two electrodes. You say, how much change you have? Let me show you this. This is a U-tube. You put a liquid just wobbling like that, like a rocking chair. And you can see the electron flow through the two electrodes, back and forth, being able to light so many lights. This means each rocking action have millions of electrons flow through that. And we first time report this one was 2014. That time we have a TNG array like this. See, we have a TNG array. You put a shower head on top. You get a light flash. We report that. At that time, we did not understand the very deep. Now, it is here. So means what? When you do chemical reaction, you can do still mechanical still. Okay, 1 day, 2 day, 3 days. Besides mechanical mixing, you have electron exchange between the rotor and the liquid. You can assist chemical reaction. Depends fast on the next one. Okay, so you can see this is something the data I show you. All what I told you are based on data measurements. Okay, it's not just a speculation, something model. Okay, this is all right. Now come to if you have electron exchange between the solid material and water droplet, can this electron stimulate chemical reaction? So in other words, water is not only just a solvent, it participated in a chemical reaction. The participation is only 200 picosecond. It did not measure before they recover self. Let me show you this principle. Okay, so this is we have a FEP polymer, and we put in a beaker. This beaker is have this magnum orange solution here. This beaker have no FEP particle. This have FEP particle. Then I'll show you what happened. After you apply an ultrasonic wave, you see the bubbles come. The one with the FEP degraded the pollution. This is a very good beginning of catalysis. Let me tell you what happened. So FEP does not have a catalysis effect. Do we know that? We know that, right? It must be some precious metal, something like that. But if an FEP particle comes with water molecule, the water molecule can transfer electron to FEP particle. After the transfer, become water ion, and this water ion combine with water molecule to become these two groups. And one of the groups is radical, it dissociates the organic pollution. Okay, so this is the first step. And this happens only within 200 picosecond, very short. Now, why do you apply ultrasonic wave? Is you have two effects. Number one, you create oxygen bubbles inside. Second one, you can kick back this electron from FEP back to the solution, because sonic wave is a phonon excitation. You excite that with sounds, and this electron can leave the surface and recombine with oxygen species dissolved in the liquid. So oxygen species combine with electron, become negative charge oxygen species. And this species combine with this group form recovered water molecule, another radical. See, this is take water molecule and this recovered water molecule form a cycle, and this radical can become the radical dissociated pollution. You form a full cycle. This is what happens in here. We call this process called contact electrocatalysis. So you have electrocatalysis, have photocatalysis. This is a different one. This is a different one. The first paper was reported 2 years ago. We will have a review recently in Chemical Society Review, published this one. So this is just the beginning. I'll just briefly tell you about what's happening. Many papers around the globe are publishing this one now. Okay, we can produce hydrogen peroxide for dissociated pollutions in nature. This is because we can use PTFE, FEP, even silicon dioxide, whatever material utilized. Same process occurs in nature. We can produce hydrogen peroxide. That one helps us to degrade. So no wonder if you have floating water, will not pollute it in one way or other. So the drinking water from the tap here, you can drink. You say why? Usually we think, oh, this is the filtering of the sand. Filter the sand will not kill the bacteria there. It's this chemical process that kills the bacteria in the water so you can drink. So this is nature of us, this kind of process. And I believe it can be beneficial for humankind, for us to study. Okay, I'll just give you a brief introduction. You can read those two papers. They give you a detail of the mechanism for that. Right? Okay, is the sonic wave the only way to excite that? I said no. You can apply ball milling. You know, ball milling is very natural. The collision between rocks can make this one. We find ball milling can also excite counter electrocatalysis and produce the species you associate with that. With this paper report, our finding. So therefore, you don't have to have a ultrasonic wave. A lot of cases, in nature, you do not have sonic wave, but you have the collision or rocks. Even that one can decide the phonons at the surfaces. All right. So this floating water can when it float in water, it can generate phonons at a liquid-solid interface. That can help you too, right? So this is a new catalytic process called counter-electrocatalysis. Here, this is the first one I show you the impact of TNG discovery to fundamental chemistry very briefly. Second one, the contribution of TNG to fundamental physics. Okay, we know the triboelectrics for 2,600 years, but its understanding remain. When we teach students about electricity, that says a glass tube rub on the surface of fur, glass tube become negative charge, the fur become positive charge. The teacher never tell us why. If you don't believe me, look at the books. They never tell you, okay, here you go, you got it, okay, here it is, but never tell why. Why is such? This is the nature of contextualization. So when you study this one, then you can find a lot more things. So there's a lack of a general model because this phenomenon occurs for solid and solid, crystalline or with amorphous, amorphous with amorphous, any material, little any material, any phase material. So it's so universal. There's no other effect and more popular than this one. So there's lack of models. So we need to go back to the atomic and molecular structures in order to propose a general model. 2008, we proposed a model. 2018, sorry. We experiment fine. So you see, why do you have to do you run this, you have to apply force. Why? In some of the area, the distance between the atom on surface with the atom on this table is so short, shorter than what? Shorter than the interatomic bonding distance. If you have two atoms form a bonding, this is the equilibrium position, but you have to press it. So this atom move towards this a little bit in a compressive, so-called repulse region. We measure with the air bond, you have to be in repulse region before this two exchange electrons. That means what? It only happens when you have a large overlap of wave function. So wave function here. So we propose a model such is that if you have two elements, they are separated too far. There's no, of course, no exchange charge, whatever. But when you compress one against the other, so the interdistance between two is shorter than the bonding length. In such a case, the barrier between two is lowered so much the electron can transfer from this side to the other side, can be transfer and transition. This is what we found experimentally. This photon emission, if we observe the experiment, let me show you next one. So you see this one, if this charge remain here, you separate the two. This have negative charge and this have positive charge. But due to temperature effect, this fluctuation, this electron gradually emitted, and this can gradually gain, reach new equilibrium. So that's what happens here. So do you have evidence to support this model? Yes. Let me show this transition here. So how do we do that? We have an FEP film, we have a quartz crystal. We put in a vacuum, we make the contact electrification. In this study, you have to be very careful because there's air discharge. You want to get rid of air discharge. The air discharge gives you an emission spectrum is broad. But now, if you have the FEP film and quartz, you can have atomic spectrum. This atomic spectrum, the line width is 1 nanometer, very thin. You can correspond well with this atomic orbital. And all this study, without going to the details, let me show what it is. If you have two materials counted with the other one, then in a molecular level, the electron can transfer to atomic level. It can transfer down more, give you photon emission. Or we can transfer the neighborhood atom transition down. That's like this, give you photon emission. Both have been observed experimentally for that. So this shows that there's a possibility you have this cross atom. porous materials, electron transfer and transition give you. We even found experimentally this have a spin selection. So if you go to atomic level, you have to have a spin selection. Of course, that's you have to be obey the Pauli exclusive principle in this case as well. So this is all thing reported in this paper here. Okay, so do support our model. The more you study, the more you find we don't know. Let me show you one. Everybody is familiar with semiconductor. You are familiar with the p-n junction. Photovoltaic is a p-n junction. So if you have a N-type and a P-type. From a p-n junction, you shining photon on that, you get the direct current, DC out. That's the photovoltaic effect. Okay? Here do different. You have a P-type semiconductor and N-type on top. You sliding back and forth. That means what? This is a P semiconductor, this is an N-type semiconductor. You just do this. This is the speed going forward, backward. This is the current measured between the electrode here and electrode here. You have a DC output. So this is no photon excitation, but due to sliding motion. This effect called triboelectric effect is due to contact between two materials, two semiconductor materials, P-type and N-type. Let me tell you the reason for that. The reason you sliding back and forth, you slide back and forth, you have to break the bond at the interface. The break bond, you have to apply force. Okay, but you see when it's slide down here, in a new region here, must form bonding. They call dynamic bonding, short time, but not that short. Okay, you see, they're short. From the bonding here, when the two daily bond form a bond, you release body energy. The body energy is sufficient to excite electron hole pairs at the N and the P interface. The built-in electric field separate that. So I have an animation showing that. This is you have an N type and the P slide back and forth. If you have two Daniel bond, you form bond immediate energy quantum, which is called body energy, which excite electron hole pairs, and the built-in electric field is separated too. The hole goes one way, the electron goes the other way. You form a DC output. Similar like a photovoltaic effect. Only thing is that is the photon excite electron hole pair. Here is the body energy released excite electron hole pair. So this is called triboelectric effect. Was first proposed. We proposed this in 2019, obviously the next year, and this is a recent review on this phenomenon being studied. So you can see if you have P and N type, you have little sliding, you can have detect DC signal. And this could be used for future MEMS devices, other devices, think about it. So, and other things to be explored. So I'm just introducing you, when you start counter-electrification, a lot of new things found. We did not realize this before, okay? Now, we have TNG with general power, as I showed at the very beginning. Can you quantify that? Can you mathematically formulate that? So that's when many years ago when Ørsted found that the relationship between current and magnetic field. Now, can you quantify that? Okay, so that's what we try to do. Okay, if you do this one for the magnetic field being cut by a metal rod, the theory for this is well established. There's nothing new you can do. Already done many years ago. Okay, this is called conduction current. There's two types of current: conduction current. As you can see, this is electromagnetic induction. Faraday's law. This is the Ørsted-Ampere's Maxwell's law. Okay, and this one, you see, this is a conduction current. This is the displacement current. When Maxwell worked on this together, he found that if you don't have this term, all these four equations does not obey the conservation of charges. So must have this term. That's when you start physics, that's how they teach you, introduce the displacement current for you. All right. So what is displacement current? Called Maxwell, he said, well, displacement current is nothing, it's not an electric current due to moving charges. It's not because charge moving, but a time varying electric field plus a medium contribution part. Time variation electric field and medium polarization term. That's it. So this is called displacement current. Our TNG works is because displacement current. That's why the output voltage is high. Okay? This works is called conduction current to give you this term. Now let's see. My goal is can we utilize this quantify to quantitatively calculate the output power we have? When I work on this, I find I cannot. You know why? This full equation was derived by assume all the medias are at rest, at stationary. Nothing move. Nothing move. But our case must involve what? The medium and the medium boundary are moving. But this thing was not include those four equations. They said, well, can we modify that to do this calculation? The answer is you cannot easily do that because it's a dynamic process. So let me show you the conditions under which those four were derived. Those conditions are rarely mentioned in textbook. So a lot of students, including myself, at first we didn't realize that. We're just teaching generation by generation for that. Okay, let me show you a little bit about this. So this is the full equation here. Everything starts from experiment. You have data to support that. Okay, can this medium motion, this kind of motion, give you electromagnetic radiation? Can we? Okay, let me show you our measurement. Okay, this is a TNG, and this is a student. He just talking to the TNG. So his sonic wave from his mouth triggered this TNG. It generated a displacement current in space, transformed here to here, being picked up by here. Let me show you the data first. Okay, see if you can see this. See the voice. Okay. Green. You probably cannot hear that. Green. He said green. Okay. When he said green, right, his voice is just triggered the TNG. So this TNG right oscillating at the frequency of sonic wave. Green. And then the displacement current generates transfer right here to here and control green light or red light. So this is just sonic wave. That means the medium motion gives you electromagnetic radiation. Okay. The second one is use a hand tapping. This is use a hand tapping this thing like that. Okay, the displacement current move from here to here. You can see being generated. Use the hand. This is low frequency. So the medium motion can generate electromagnetic wave. However, those are never calculated by the original equation because those four equations derived by assuming no medium motion. So let me show step by step. Okay, let me skip this. If you look at the four equations here, if you have a closed surface, this means that flux through this closed surface is the total charge inside. That's what this means. Okay. The magnetic flux through a closed surface is zero. That means no magnetic monopole. What this is the magnetic flux through an open surface. Its changing rate is the electromotive force around this edge. That's what it is. Okay, it's called circulation. Circulation. If this is an open surface, and then this is the differentiation of this magnetic flux. If you do one more step, this is differentiation applied to the field, differentiation applied to the integral unit. You have these two components, to the field and to the surface. Now to make it simplified, they assume the integral surface does not change, so we can drop this term. Then it becomes this term over here. On the left-hand side is the line integral. This is the circulation to a surface integral. This is the Stokes law mathematically. There's nothing new here. So if these two functions function here and here, this holds for any loop. These two functions must be equal. So this is the third equation in the Maxwell equation. So all the equations derived assume This surface does not change. Its boundary does not change. Its distribution does not change. That's where the assumption is. Then we forgot about this assumption in the textbook. We just read. Okay? So now, if you have this term, the expansion velocity of this surface will matter. Okay? How much matters? I will not go to detailed mathematics. I'll just show you this is going to be matters. It's a velocity dependent term. Now, that's this term. If you change it, if you have a rotor like this, okay? Now, if you talk to the power people who are working with power people, they convert the mechanical energy electricity, use the rotors here, and the rotation, moving object, they must have this term. If you know this term, there's no output power whatsoever. If you talk about communications people, they say we don't care about how you generate electric power. If you have an oscillating current, I can generate electromagnetic radiation. So communication people is worried about this, assume no medium motion. Power people must have medium motion in order to have power generation. So those have two different assumptions. Therefore, they are unable to quantify the electromagnetic radiation in the vicinity of a power plant. They cannot quantify that because there's two assumptions here. Okay, now how do we do it? So we need to consider the body, this medium rotation here, as I stated in the previous PPT. Without going to detailed mathematics, let me show you what we found. If you work on the medium motion in the equation, you have this term. This come in. This the rotor is rotating. Okay, you come here. But in the classical physics, they assume this is the full equation. In order to consider moving charge, they say you have to put the Lorentz force. But in fact, this law should cover Lorentz force. So if you put these two together, this is automatically Lorentz force in the equation here. The only thing this does not appear as beautiful as what you expected. The reason because in engineering was nothing is beautiful because we have to work, we have to make work. That's what it is. But mathematics want to make it beautiful. You can forget about this term. Okay, this one let's assume for universal thing. Okay, so this is the one. My goal is that can we utilize this to quantify our data? All right. So this is my goal, and I'll show you we utilize 4 equations to replace the role of these 5 equations as listed in the classical textbook. Okay. So now, if you have a rotation object, if you have the stationary Maxwell equation for electromagnetic emission here, for the whole space here, you have this term here. That means if you have this rotation, you must have, because this term, they give you this one. You have to consider that, right? So I just tell you where it comes from, and you have a good idea. It's not just added on one way or the other. Okay. So a lot of theory, if you go to the detail, find if you put in equations, must have some assumption on the back. Right? Must have back. If you don't have assumption, you cannot make a simple term to run mathematically for that. Okay, so this is the electromotor and Maxwell equation. So we can put this all together. To make this simple for you to memorize, let me use an analogy. It's like a person who threw a disk. This disk have a translation velocity and a rotation velocity. Right? If you watch the game like this, inside this disk, because the rotation medium, you must have this term in a differential equation inside the disk. But outside this, in the free space, you have this set of differential equation here. But the solution of this 4 equation and the solution of this set of equation inside the disk, 2 set of equation meets at the boundary, at the surface. So therefore, the rotation of this disk through this term will affect the field distribution outside. So if you do calculate, you'll be able to do that. So this shows that if you do this in more detail, you find a truly moving object can affect the electromagnetic field for here. Without further one, if we use this equation to calculate the TNG output, will become more realistic. This is 9 TNG, 1, 2, 3, 4, 9. the inter-TNG distance and the side length width have a ratio. And if we use our theory to calculate, we find it was the maximum. If you're too close, they're not good enough. Too spicy, not good enough. They have an optimum, and the experiment found there's agreement one way or the other. So therefore, we begin to make our data more quantitative, more approach. We can predict and calculate that. So that's the purpose. We work on those theory, enable to quantify the output, improve the output, of course, optimization of the output. So this just show you this sort of TNG has many impact. This is good enough. Because I don't want to talk too much about the theory, other students will feel very boring about these things. Okay. Now show you the impact of TNG to current technology. What technology can impact to many things. If you look at robotics, if you can look at rotation side TNG, through organic materials, you can design self-powered sensors for control, for angle measurement. You can reach a sensitivity of nano radian, nano 10 to the -9 radians, because the output signal is so large. This is for robotics. You can work for robotics for the sense application, right? So this is one I like to. Second one, and if you put several sensors on here, you can do a voice recognition. Let me show you. And this person talk, and because his voice, those sensors.
Open sesame.
Okay. So this sensors put on his face here and sense the
Open sesame.
voice. Now, if he does not have a voice, but have just a jaw motion, muscle motion, what happens? And this can identify his muscle motion as well. This will show you. So we use this one for a lot of machine interface and as well. So this is motion detection.
Nice to meet you.
Right. Okay. So this is one. Right. So you can detect the motion, very tiny motion here. Okay. Fabric. I was traveling in Sweden. They have a lot of cellular materials. Here you have same thing. Cellular material based fiber material is the ideal material for triboelectricity. We make this one, and you make a carpenter to be as a sensor array when you put on floor here. So this is another field you can look into for textile fiber people, right? For fiber people, they will look at this 3D woven TNG as well. You can also put this in on the floor. A person walking through it, you can detect a signal, the trajectory when you move in. You don't need to apply power to this carpet here. You only just walk through to give you the signal. And this means what? For healthcare, for elderly people care, for security, you can utilize this as a supplement to that too. Just walk through, there's a signal being detected, right? And without good detail for that, you can imagine a lot more in your daily life. Anywhere, any time you go, you have this effect. If you play ping pong ball, any sports, you can identify a valid ball or invalid ball, because sometimes use this trigger sensor here, you can measure the signal immediately. If you don't know triggering, there's no signal. If you trigger it, there's a signal. Immediately measure for that. And this signal is a volts, so easy to be measured. So we utilize such. We developed many things for smart spots. Okay, and also for power lines. If you go to this 100 miles, so high, so long, in a remote area, the operation of infrastructure relate to vibration of this cable. So measure temperature, vibration of the cable, as well as tension, sometimes the tension. The third one, also ice buildup, is good for the safety of a power line. You'll be able to do that through this just the power line. That we have a little gadget you hang on there that measure for that. Okay, so this is for power line security. Even work this for infrastructure, bridges, and everything. You'll be able to do that. There are too many applications. I'm unable to cover everything to you, and because we recently finished editing this set of books called Handbook of Triboelectric Nanogenerator, 2,000 pages. You can see from 2012, one paper turned out today is a 2,000-page book for you to look at. So I am able to cover the whole thing that is for medical, security, human-machine interfacing, wearable electronics, you name it. Anything you can talk about that. One word, as long as the motion, you can either serve as a power source or have a sensor. Anywhere, if you so as a human, this is a common characteristic of our motion here. So this is the, without go further one. This is how good you can do. People always say, okay, can you make how good is the one? If you work on this 3D integration, this is not only just surface technique, 3D integration through the rational design, you'll be able to have an instantaneous output power density reach megawatt per square meter range, very large, at a very pulse. So you'll be able to do that. And this shows how good you can do the power density. The efficiency, you can do very well too. The efficiency, even 10 years ago, which 50%, 50% or larger efficiency. That's we'll be able to achieve that through many of our study. This is conversion efficiency. You can see that this is conversion efficiency. Depends on the design you have, and this is sort of one of our indication for efficiency over many years. Okay. Now is industry product. So let's. I talked to Professor Yue yesterday. He asked me how many company you are, how many company you going to run that. Some larger company like in Korea, like Samsung, and also in the U.S. Several national labs like Pacific Northwest National Labs, renewable energy, as well other labs are doing this towards the true application. Let me give you examples of something we have done. Okay, we have incubated about 10 small companies ourselves. Many on medical, health, environment, solar power security, and microenergy and blue energy. Okay, let me give you examples. Pacemaker. We work on 11 years. Use the breathing of an animal. Such a small device, the breathing can harvest energy sufficient to power this pacemaker. This took us 11 years to do that. Okay, so we want to make a pacemaker so powered. This can open door for implantable medical devices with a benefit to humankind over large. Okay, even this can be used for brain stimulation right now, for brain disease treatment. This is the beginning. Okay, we thought this was 2009. This is the result we got 2009. We'll get a lot more recently. The next generation pacemakers, no cable. Is this inside the heart? They have this little device, which is very little tiny, which is about 2.5 centimeter long. The diameter is 0.5 centimeter or even smaller, very little tube. And it wants its lifetime to be 30 years or longer. 30 years longer. One of the key challenges is the power. Does no battery be able to run that long? So we need to build in a limited space for power harvesting using the dynamics of the heart. So this is the next generation pacemaker. We try to make self-powered for that. Okay. We also make this Chinese medication. It's a medication we try to apply for detect pulse. You know, there's a pulse they can detect for that. Through the pulse, you can analyze the fluid dynamics, can predict a lot of things associated with health. This is one we try to build a platform for people to use. The other one is human-machine interface. We build a keyboard. On each key, we have a TNG. So you strike the key. The key can give you the voltage, is the amplitude you strike this key. The current gives you the speed at which you strike the key. So all this data are recorded. So you have this 8 fingers typing can analyze the dynamics of your typing. So not only you have to input the password correctly, but also the way you type the password has to be correct. They say, well, if I do a little bit of other things, I may not type the correct one. The machine study you because they build this, they try to understand your characteristic view. So even you have some deviation, you find. So we do the training. You type this your password 50 times. They any way you type, they recognize. So this is called machine learning for that. Okay, water meter. Every family has the measure of how much water use, how much water flow, the pH value. So we use the water flow to generate TNG water meter. Measure the water flow rate, pressure, speed, volume, as well as pH, even impossible chemical solution. So everything in the package, and this now can send a signal wireless to the cloud. You can build this as an app. So this is the thing we are monitoring what gas and oil pipe over large. So you have a city, each have this one, you'll be able to you can do a lot of emergency measurements. You can also do the decision making. So it's not only just know how much you pay for your water. That's just very basic. But if you want emergency something happen, you'll be able to do that. Vibration. Vibration is the key thing for infrastructure like bridges, old houses, some civil structures, anything, you have the vibration detector. Even transportation, rail tracks, you need to detect that because if some screw loose, you don't know. And I was to go to travel in the Luleå University. They have a big center called tribology, and one is called is the bearing, and they have machine that have bearing. The bearing, if some loose or some of the ball inside broke, they need to know that. So use this technology that can measure the vibration from the bearing. You can know that something happened inside. So for safety measure. So you can see in industry, a lot of needed to be utilized for vibration detections. You can use the energy comes from vibration for detection any kind of abnormality with the vibration. All right. Air filtering. We use the triboelectric effect for air filtering, so we produce the filter, no ozone emission, no waste materials, as well no pollution as well. So this is the one, and we use the triboelectric air filter, even now sold in the market for subways, hotels, etc. Okay, so all these things is open one TNG open law. The company called NER TNG. That's what the name, right? Okay. For medicals, recover patients, all that's what you need to be tested in a hospital for patient recovery for that. So anything you can name it as a motion related for that. Okay, and also we have the built self-power shoes. If you put the shoes here, you're walking, then pop energy harvest do a GPS positioning as well as tracking purposes. So the TNG data shoes would be manufactured for that. So those ones are the examples. Another example is turbulence monitoring. If you run an aircraft, you have a lot of turbulence. This is the cross-section of an aircraft wing. And when you do that, you find that turbulence occurs. But how do they know, study the turbulence occurs? They use very old-fashioned way to measure, which is such. Let me show you. In order to see the turbulence here, they put a little strings on here. They're going to see how these things flow. So you can see this is not accurate, not scientific, not digital at all. How do you can ask the turbulence? So we put our TNG on the surface wing. We use the counter-triboelectrification effect to identify the amplitude, the speed at which the turbulence occurs. And this is the first generation. We have made a third generation already, which is from a small company to manufacture this one. And now it's much better than this first generation here. Okay, so this is just for flight safety. If you have a large environment like here, monitoring the gas emission, carbon monoxide distributions, just gas analysis, you can place over there, use the breeze wind, generate electricity to build a solar power sensors, so all the signal can send to the cloud, right? So this is the solar power sensors. We have many challenges, but of course, people always ask me, you can make this lot longer. Per your need, we can make a last much longer, and we can use different switch mode operations, because this sliding, we don't have to do this all in every cycle, because when the charge goes on, this remain there for hours. So we do a little bit of spring design. After 10 cycles, it's lift up a little bit, so you can free rotation without wearing, but still working as a TNG for that. So many modes we can do that. I even use lubrication oil. You can put lubrication oil right here, and we find in many cases did not degrade the performance, but in contrast, it's improved the performance. So improve materials resistance, wearing, etc. All this together, we can make a lifetime change much better. Lastly, how can you contribute to the human sustainability over large? Is it possible? Okay. There's a report from the European kind of science and Chinese kind of science. They found the ocean energy substitution for fossil energy. Ocean energy substitution for fossil energy could be the future one. But this is a too challenging a task. Too challenging task. Now, how do you do that? Well, say ocean have a lot of energy, but vast, complicated, expensive. How can we do that? So this is an example of high entropy energy. Energy is there. It's just not in the form you need. Okay, so can we do that? So 2014, let me just say, the energy we have different one, tidal energy, wave energy, but now current technology utilize still electromagnetic generator because they don't have other effective magnets to do that. So the invention of our TNG provide an ideal choice for harvesting wave energy in ocean, because the way we talk about this one is not big wave, we don't have big wave, just normal like wave here. Okay, you see here. Okay, how we do that? So 2014, I wrote an article say if you have a shell core inside the shell, this rolling back and forth, you'll be able to have to generate electricity. If each unit can generate, we make a networking, like a networking, 3D networking. We can integrate all this output together. This could be an approach. One layer is not enough. One layer is not. We can make 2, 3, multiple layers below. So we call this called blue energy. So that was just a proposal. Now let me show you from this idea how far we moved forward. The traditional technology cannot do it is because the voltage depends on the frequency. So when the frequency is low, the output voltage is so low, unable to output anything. And we can do it because we use organic materials, we can float on the surface. Because this one is always sink in the bottom. You cannot float on the surface, it's too heavy, the density is too large. Now, if you have this is the operating frequency, this is the output of TNG from this, and this is the output of EMG. This is many times better than EMG in low frequency. So therefore, this is a zone in which the performance TNG can much more far superior than EMG. So we try to do that. We find this is 16 balls rolling back and forth. You can find that it works. You can do that. All right. So this is the beginning. We try to do that. This is we show this possibility 2016. Now, if you have a rotation disk, you have a pendulum drive here. If you have 10 layers integrated together, and this is what you get, right? So then we have like this. You have a slow motion, you have a fast motion. This is such an output that you are unable to do that from electromagnetic generator because the pace at which you cut the magnetic flux is not enough. Okay, so therefore, this is the zone. This is some kind of scenario in which we can apply our technology. Right? I'll show you a video like that. So this 3D integration, one unit is not enough. One solar panel is not enough to solve the power need. But if you have many panels, you can do that. So if you put a ball inside ball, put it here, we could do that, right? So therefore, look at this one. We have at least we have a approach able to half energy over large. Okay, so ball inside ball for that. How much efficiency can achieve if you design the structure correctly? The total, if you hit this pendulum, the energy conversion efficiency, total energy conversion can reach 28%, even higher. And so we have a structure design and also surface design. So you treat this once, it can oscillate many times many seconds before it stops. So all total energy can reach from all the cycles integrated together can reach 28%. Remember, you are harvesting low quality energy. You don't expect you have high efficiency. That's what you have. Okay, you don't expect that because it's not like a power plant. You generate burn coil, and you have a large power because this is what you have. It's a low power density, large volume. Okay, let me show a real example. A year ago, we manufactured this module. So you can. This is a module. We call nanogenerator, but when you make a integrate together, it's not a small thing anymore. It's many component inside. So we make this module. We put on this light tower here. Okay, light tower here. In the ocean here is floating. It's floating like that. And a year later, after they can charge the battery for this lighthouse naturally. So we took it back and we measured lab just a month ago. It works well. It's still working after surface in the air for surface in the ocean for a year. So you can see when the wave come in, all right? This is the wave we talk about. You can see the wave, right? This means the future. So while people maybe say how much you can generate per cubic meter water, we can generate 80 watt of power, peak power. On average, 13 watt. This is more than twice of electromagnetic generator. More than that. Okay, so this is the beginning. Show the possibility, and even make a seaweeds. You'll be able to generate from seaweeds like that. Most people have such
Ocean waves can be powerful, containing enough energy to push around sand, pebbles, and even boulders during storms. These waves could be tapped as a source of renewable energy because wind and solar power aren't suitable for underwater applications. Wave energy could someday power floating buoys, lighthouses to help ships navigate, or underwater power stations. Now, researchers reporting in ACS Nano have developed flexible power generators that mimic the way seaweed sways. These generators can efficiently convert surface and underwater waves into electricity to power marine-based devices, such as the blinking LED lights at the top of this buoy.
So what's the future choice? We have solar, we have wind, we have TNG blue energy. If we do well, the output of TNG may not be lower than solar and wind. But the future is that if you have wind, you have solar, you have blue, you have a hybrid system integrated together. You can use whatever you can, wherever you can, and you'll be able to have a total solution for the energy. A single one may not solve the energy we need, but you put them together. So this is called hybrid energy approach. We hopefully in the future we can be able to do that, and we work on it right now. We should have full confidence with the future. And when we first invented this one, people always ask me, how much the cost? So we did the cost evaluation 2007. We found compared to solar and nuclear, if you optimize, it's on low end. When I was a graduate student, 1983, 84, I had to calculate. That time, solar panel was the only thing I can remember that time that can power. That time, do you believe this is going to be a major power for the future? There's no way. When I thought this is a little calculator, we can afford it, right? Now, they can do this. And cost reduced dramatically. When you use MOCVD, make LED lighting, so expensive. $2 million machine make a little wafer like that. How many LED light you can make from that, right? That time you hardly imagine we can use this today. This LED display panel, you can utilize that. Many years ago, you think this is impossible, too expensive. I remember the early day when you used the LED for lighting was just Christmas tree. That was about it. But today's lighting bubbles use that. Oh, wow. So be positive, be looking forward. You never realize the potential of a field as time goes by. People will find a way to reduce the cost, to improve the performance as integration. If you ask me now, I need a lot of resources to do that. I bet this is from here to here. There's so much things put in that, right? So a lot of effort in that. Okay. So in the world, there's Now 16,000 scientists in 83 countries regions who are engaged in research and cell power systems and positronics. Every year, a few thousand papers being published worldwide. So this is a show broad impact. I traveled this time, 5 years ago, I traveled in North Europe. Nobody was doing TNG. There was nobody. This time, also Uppsala University, there's a couple of groups doing that. They recently published a paper on that in Science magazine. And also with the Middle Sweden University have 5 faculty working on that. They want to talk to me about teaching student courses and have a local conference. I went to Luleå University, they do on the tribology. That time, 4 groups work on it too. Then I will go to KTH and other. Our founders faculty work on that too. So you can see, this time we have a symposium in the European MRs and Strasbourg at the France. We have, for the first time, we have a symposium on nanogenerator. 150 people in that symposium, not the abstract. I was very encouraged by what I saw. So 5 years ago, nobody know what this is, what we can offer. So I'm coming here today. I hope can inspire some people, can possibly plant some seeds here that something can offer from this technology. The future you may not realize now, but do look into this one. Okay, do look into this one. So note, as the chairman introduced, no wonder that they have an evaluation about the things for that. This is just regard. Okay. Summary. Today I talk about the TNG from the beginning. High-entropy energy broad. The invention of TNG set up brand new technology which can bring potentially some great impact. So I talk about its impact of chemistry. You know, chemistry talk about the charge transfer between liquid and solid, also electrocatalysis, as also the use of liquid and solid interface for power generation and sensing, which we were unable to do before. We'll also talk about study the quantification in solid and solid, a model for that, as well as potential bring the idea, how can you quantify the output, bring the study on the expansion Maxwell equation for that, right? So all these things, we did not think about it before, but once we have new experiment data, you try to understand it, try to quantify it. Furthermore, if you talk about technology, if you can work small power sensors, motionless sensors, you have a broad application. If you can make a large blue energy possible to reach the theoretical expectation, there's a lot of things to offer. We can imagine for the future. So I think this is a big area, this is a huge area, have a broad impact to almost all the discipline in engineering and related to, especially today you talk about artificial intelligence, these Internet of Things. If you have no big data, you have nothing. Nothing. So you have to be so the sense is a fundamental one. If you have no big data, all this just talking. All right. So finally, I also bring the potential application for industry. Well, that's just a few mind case. You can think a lot more than what I think because my knowledge is limited. Only limited what I can think. You can think more for that. So I think this opens a brand new chapter for many people over large. So this is a summary of my talk, and because I talk fast, if you want to look at some of this review articles, you can look at this one. This is solid with solid, liquid and solid, TNG overall, and also triboelectric effect and counter-electric catalysis effect. So all these things, you can look at the papers for that. I even have a couple of videos on YouTube for that. So this is the YouTube on the Maxwell equations, YouTube for the quantification, all this one, you'll be able to get that, to watch it, give you a more detailed explanation in different languages. So, okay, right. With that, I like to cut short. I thank you very much for giving me this opportunity to come to this beautiful camp for the first time, and also to meet some of the students and faculty, and I look forward for more discussion with you and possibly collaboration as well. Thank you very much.